And I want to talk right now about, not specifically about RavenDB. I want to talk about the sharding architecture of RavenDB. Now, if you aren't aware of what RavenDB is, I'm going to spend just 1 minute or two to explain what it is. It is a non-relational database that allows you to store data in JSON format, query it, operate that, and in general part of the NoSQL movement, although it actually has a SQL query language support for C#, Link, a whole bunch of other stuff, but basically it's a database, it's smart, it gets out of your way, and that's about it. You can see what it looks like here. There is livetest.ravendb.net, and this gives you access to a public instance. Right now, this has no users, no data, but now you can see that the data itself is just JSON. But the key advantage here is that we are able to run queries such as it would help if I actually remember how this works. And now I get all of the orders that are actually being shipped to London and things of this nature. Again, I'm not going to talk about RavenDB. Assume that this is a database and we'll move on. I do want to talk about sharding with a lot more emphasis. So before we start, I want to talk about something quite interesting. What is sharding? And I am enjoying these talks a lot more if I have people who are talking and discussing, asking you questions as we go along. So feel free to interrupt, raise hands or whatever, just ask any questions that you have. So what is sharding? Sharding is the act of taking a database and splitting it into multiple nodes. Now, why do I want to do something like that? And the answer is that I want to do that to be able to have some part of my data in some servers and thereby have increased overall capacity. So let's say that I have a server that can contain, for example, I'm holding here a Raspberry Pi. This is a small server. And it can actually, let's say, host 500 requests per second. I need 15,000 requests per second. I cannot handle that on a single server, so I have to scale out. And that is part of horizontal partitioning. It gives us a shared network architecture, a whole bunch of other stuff. But this is not new. This is something that existed for a long while. But I want to take you back a bit. I want to take you back to 1994. In 1994, every computer that you had would typically have a drive, which would be this 5.5 inch floppy disk, which was a real floppy. And then you have this 3.5 inch drive that was typically the B drive. And when you talked about big data, you went to this book, which is actually a fascinating book, still relevant in many aspects today, that talks about managing gigabytes, because that was an obscene amount of data at the time. But time changed, and let's do a short time skip. And now we are at the beginning of this millennium, 2000, 2010, and we are past the dot-com boom and bust. We are now looking at many companies that are thriving on the internet. And we run into problems with scaling the load. We have too many users, too many queries, too many requests on the system, so we have to split it up. Now you can add web servers very easily. Web servers generally don't have any meaningful state. So we just add more of them, but they need to access database. And the question is, how do you actually manage scaling up the database layer? And the way to do that was to shard the data. And you can see here a great example. So I have multiple distinct database servers, and I'm splitting the data among them according to some rule that I have. I actually was involved in a sharding project all the way back to 2005. Now, at that point, I had two specific customers in mind, two specific use cases in mind. One of them was indeed very big databases, but at the time, SQL Express, Microsoft SQL Server Express was limited to 4 GB or so. And I got a client who wanted to be able to run SQL Server, not pay, and avoid the 4 GB limit by running multiple database servers, or actually multiple databases on the same server. Now, this is actually quite interesting because the problem here is that, okay, I have multiple different database servers. How does it help me? And it helps me in the following way. Sharding isn't just about splitting the data. It's about giving you the behavior that making it look like you can still query across everything in a consistent, easy manner. So it's not just, oh, I know that for all of the users starting with A, I need to go to this server. All of the users starting with J, I go to this server. The idea here is that I'm able to issue a query and there is some layer between the physical data and my application that can do this translation. This is what sharding is all about. But before we dive any deeper, I want to discuss something quite interesting. And this is the typical hardware that you had for servers at the time. And more specifically, I want you to look at this guy. This is a hard disk. It may be something that you're no longer familiar with, but this is more or less how it works. There is a platter, there is this needle, and you read data from that. And the speed in which you can read data from the hard disk depends on the number of revolutions per minute. Now I want you to see what happened when I translate those numbers, 15,000 RPM. That sounds a lot. That translates to 250 random IOPS per second. What does it mean? Look at this needle. I need to read something from here. This spins at a rate of 15,000 revolutions per minute. That means that this spins at a rate of 250 times per second, which means that if the head of the needle past this, we have to wait for it to go back. Or maybe I'm now looking at here, but I need to see the data here. So there are physical limitations to how fast I can read and write. Okay, so we'll keep this in mind. 250 IOPS is the maximum number for high-end hard disk. Now I want you to look at the very first EC2 machine. It's so new that they didn't even have any concept of instance types and stuff like that. Just a machine. That was the EC2 machine. Look at that. 1.5 gigahertz, 1.75 gigabyte of RAM. Not no good disk, but that was typical server hardware in 2006. What does it mean? That's the sort of things that you have to build applications. So think about what it means in terms of how can I actually run big systems on that. That's actually quite hard because if I'm running on this hard disk, I have a maximum of 250 random reads or writes from the disk, limited by the physical hardware. And this is the under 2 gigabyte is a reasonably spec'd server. So the physical limitation of what we could squeeze into a single box is highly limited. And again, server software at this point. So people started going with shards. So instead of working on a single machine, you work on multiple machines. Instead of one hard disk, you work with multiple hard disks. But now we are in this interesting position. That was many, many years ago. So what happened if we fast forward, let's see what is the current situation. And this is what we have. I can go right now and spend under $1,000 and get NVMe drive, terabyte range, and look at those numbers. I'm drooling at those numbers. I'm a database guy. Those are just amazing numbers. And compare that to a hard disk. But notice this is the gigabyte per second. This is the megabyte per second. That's sad. By the way, if you take anything at all from this talk, if there is any possibility, go and use NVMe drives for production. If not, use at least a good SSDs. Never use these for production. That's just, there is no real point of doing that. So now we are in a completely different ballgame. Now, if you remember, there used to be this sort of thing called Moore's Law, where we said that every 18 months, the size of the size of your CPU would double, number of transistors in the CPU would double. So it used to be the case that, okay, in 2000, I have 800 gigahertz. In 2001, I have 1.6 gigahertz, stuff like that. This is no longer the case, but I'm going to give you a simple example. Here I have a pretty sad machine. Again, this is this guy. This is a Raspberry Pi 4. It has 4 cores, 1.5 gigahertz ARM, and 4 gigabyte of RAM. I plug that into a 2 terabyte SSD, and I use a data set that is in the terabyte range, and then I hammer that with requests. And I was able to process 500 requests per second with latency where 99 out of every 100 requests would complete in under 200 milliseconds. And that's not good. Make no mistake about that. That's not good. But this is literally disposable hardware, and I can get so much more than that. If I go to real hardware, and this is again not insane, just reasonable amount of disk and cores. This is low-end disk in Amazon. This is actually a disk that is slower than almost any other disk in the market. But I can do 30,000 requests per second, where only one request out of every 1,000 would be more than 200 milliseconds. And if I change that to a better disk, I would have 0 requests that exceed 200 milliseconds. Now, this is on the low end. I can go to this guy, 128 cores, terabyte of RAM, and this ridiculous amount of fast disks. So why go to Sharding? Why talk about Sharding at all? Why not just get a bigger machine? Can you give me some idea on that? And sorry, apparently I messed this up. Why not just get a bigger machine? And there are a couple of answers. The first one is that we used to think that data sets in the gigabyte were big. But now data sets in terabytes aren't uncommon, and it's relatively easy to get bigger, to get a situation where you have bigger data sets. Other options may be related to data locality. For example, if I have users in the States and in Europe, I have to consider the GDPR. There is a similar law in the UK. And so I have to put UK users in the UK. I have to put European users in Europe. And I still want to have this nice model of how my data looks like. I may want to just partition the data for some other reasons. Maybe because not necessarily regulatory concerns, but maybe I have, oh, here is the games data for the Asian server, and here's the game data for the South American server, stuff like that. Another thing is that I can parallelize resources. That's sort of the case, and we talk about this in a bit. We have Travlos here, I hope I'm pronouncing that properly, probably not, talking about cost as a factor. And that's actually a really interesting note. Cost is actually not a factor. Take a look at this. I can get 4 M6A2 extra large, and that will be the cost per month. Or I can get 1 M6A8 extra large for the exact same amount of money, which is really strange if you think about it. It used to be the case that as you got bigger machines, the cost would go exponentially higher. But now I need 4 machines of 8 cores or 1 machine of 32 cores, same price. So why do I want to go with Sharding? And there are a couple of important factors. One of them is actually the data size. The other one is that I may need to hit the actual limits of the system, at which point I have to go to the disk. And disks have finite capacity. Let's go back to this guy. I have 30 terabytes on this machine. What happens if my datasets exceed 30 terabytes? Well, I can get more, probably. I can use an EBS drive, but eventually, even EBS drive has the limits. And good EBS drive, what you need, because if you're running a database, you care about performance, so you probably want to use NVMe or similar, which means that you're using something like IO2 in AWS, or maybe you're using a provision storage on Azure. They are expensive. And I will repeat it again because they are really expensive. So it's tend to be cheaper to get multiple separate disks and get parallelization through that approach, aside from the actual total capacity. So here's an interesting observation. RavenDB had sharding since 2012 or thereabout. And in 2018, we removed that support. But why? Why remove support for something that is obviously useful? The answer is that it isn't actually that obviously useful. Again, because of the scale in which you're working, the hardware that you're operating. On a Raspberry Pi, I can handle terabyte range datasets quite easily. And getting machines that have a terabyte in RAM isn't that hard today. So the actual need for those sort of for this was lessened, not removed, but reduced. The other side was how we implemented that, and we implemented that from the point of view of the client. So each client would have to have the sharding strategy, would have to understand, but I will talk exactly how it works later. And when you have that on the client, then there are administration issues with how you manage and how you work with that. So we couldn't, and sharding is quite complex to implement properly, especially to the level that we want to do. So we said we're going to defer that. And now we're on the stage that we re-implemented that. And now that's what I want to talk about today. So let's talk about this like this. Here are the things that I need. Admin has to be able to operate everything. It has to be easy to set up and understand. It has to be running on the server side, and it has to use homogeneous system. Now, what's the point? Did any of you ever had a chance to run a sharded environment? Did you run any big databases that was running on multiple nodes? And if you look at the industry at large, you have Elastic, you have MongoDB, you have a Couchbase, all of them have sharding built-in, but they tend to encourage you to use them at a far smaller size than you would need with RavenDB. And And let's get to Couchbase as a great example. Couchbase would shard the data, but then when something changes, you would need to reshard the data, which can take forever. With MongoDB, then you have the MongoD and MongoS processes that are running, and the network topology becomes quite complex. This is who my admin needs to be. I need to be able to set it up and run, and everything should just work. And now I'm going to do something that I find quite scary. I'm going to do a live demo. Before I do that, I want to explain why it's scary. I literally went yesterday and grabbed the latest code, run it, and now I'm going to show that. This is not release. This is not even the point where we are presenting that to customers. This is just whatever we had in the repository at this point, and we're probably going to run into some issues, so bear that in mind. This is not the final product. I do really want you to give me your feedback and how and your thoughts on the matter. So I'm going to go here, and this is the database. It's running. We don't care. Here we have this sharded demo database. I'm going to kill it. I don't like all databases. Let's create a new one. So now I'm choosing a replication factor of 3, and I want 3 shards. And I mentioned that we will get errors. And now I'm going to create some sample data. Now you can go here, and in a few minutes, we're going to see here's some data. This should be very similar to what we saw before. Here is the data, a whole bunch of stuff. What is interesting here is that how this looks. So I have a total of 1,000 documents in this system. But is this too small? Do you want me to increase the size? And now you can see something a lot more interesting. I have 3 shards, and each shard 0, shard 1, sits on multiple separate servers. Shard 0 is here, shard 1 on node B, and we have, apparently we need a scroll to go here. It doesn't let me. And what's the point? You can see that here the count of, so this is shard 0, this is shard 1, and this is shard 2. Now in this case, I set it up so I have 3 servers and 3 shards, so all of them resides everywhere. I would typically set it up in a different manner where I have multiple shards and multiple nodes that cover everything. But we discuss about high availability and everything later on. Now, what's the point of that? I can now go and create any document. A document will be created. It will be on some shard. I don't care or think about it. But now let's go here and go to one of those specific shards. So this is shard number 1. And you can see that I don't have here any users. Shard number 2, still no users. Here's the user. So effectively, I have different views on what's going on, because here I have users, but it only resides on one shard out of the 3 that I define. But again, this is as I defined. The whole idea is that you get this virtual behavior, virtual view of how things work across multiple servers. It gets more interesting when we start running queries. By the way, here you can see the state of this index across all of the nodes and all of the shards. This is somewhat repetitive, but I can do a bunch of work, and that sometimes is interesting. But before that, let me show you. I want to ask a question. Where ship to city is London. And now I'm going to get 33. If I would go and run the same query on 0, we'll get 14. So you can see something quite interesting in this regard. I'm able to issue the query, and the server know how to go and get the data across everything. I don't need, and it's actually quite hard at this point. I mentioned that we aren't done with the work, and a lot of the work that we are still missing is in the niceties of how to actually make it apparent what's going on across the UI and everything. Okay, I was here. So let's talk about a couple of concepts. Though you can think about those as buckets, and RavenDB shard them based on the document ID. RavenDB internally has 1 million buckets, and we split those buckets based on the number of shards that they have. And we'll see how it looks like in a bit. The idea is that each shards own the set of buckets. And now we can go and look at the actual cluster and understand what's going on. So right now you can see I have 3 nodes in the cluster. What's going on? Each node serves in several capacities all at once. First, it's the standard database that we saw that with the $1, $2, $0. It's the sharded database that we also saw, but it's also the orchestrator. Whenever I get a query for a sharded database, it goes to the orchestrator, which then decides how to execute that. It may decide to send it to all of the shards. For example, if I'm running this query, then that would go and hit all of the shards. I think that I can actually show it to you live. Okay. So I can see something quite interesting. Look here. Here, I issue a query. This is the query that I run on the demo database. And you can see the underlying query that went here to demo number 1. And let me go to node C and node D. Clear, clear, clear. And now I'm going to run this query again. So here is the query to demo 0. Here is the query to demo 1 and demo 2. So effectively, we have the orchestrator in the middle that is managing and processing all of those items. The reason for this architecture, and I want to take you back to here, is that I don't want you to think about it. An orchestrator is a database for all intents and purposes. It just happened to reside on multiple servers. Okay, let's go a little bit deeper. I mentioned that orchestrator is a RavenDB node, and you can use that either to just process queries or just manage the sharded infrastructure or to actually hold data. Our expectation is that you're not likely to have separate data-only items that you'll have, that everything is going to reside in the same location as a set of homogeneous services. Why is that? Because if all nodes are the same, you don't have to think. Everything just works. So we accept the clients, and this is important. The clients are not aware of sharding. So I can write my code using all clients, using everything that you want. And at some point, I can switch over to sharding if I want to. The entire responsibility is on the server side. and the operations, the management, the administrators can manage that. Now, let's go a bit deeper and see how it works. So this is how we do the hash, sort of. We have the document ID, we run it through a function called xxhash, modulo 1 million, this gives me the bucket ID. And so this document belongs here, this document belongs here, etc. A shard or a node owns a certain range of buckets, 0 to 300,000, stuff like that. So the idea here is that from the document ID, we can find the bucket ID and then the specific node. So this is an O1 operation. This is really fast. Now, typically, document IDs are something that are generated in some manner. Sometimes they have meaning like this, but they are unique in this case. Sometimes they are just some numeric value or random, whatever. The idea here is that because we use the document IDs, then we can split it up in an even manner across all of the shards. And that handle a specific issue of how do you split the load in a fair fashion. Because one of the dangers that you have to deal with shards is what happens if all of your big customers are in New York and your New York shards is really, really busy, stuff like that. Another thing to notice is that this is always done on the document ID. But RavenDB actually can do a lot more than just store documents. So you have here documents. Here you have past versions, and you can see the history of changes. Documents may also have attachments, such as this one. So some binary attachments, time series data, a whole bunch of stuff like that. And okay, I mentioned that we'll get errors. And the basic idea is that everything that belongs to documents resides in the same shard because the document is the unit that you're typically working on. So that's great. And that means that because we use the document IDs, then we don't really need to think about that. We don't have to have a complicated sharding strategy. How do I move data to here? It just works and it does the right thing by default. The problem here is that you also need to do, sorry, I messed up the presentation when I changed the theme recently. So here's the deal. Sometimes we need better control. So how do we do that? So we shard by the document ID, but we aren't limited to just that. So you can see this yellow one. This is the shard. This is the document key that I would feed into the sharding function, the xxhash and the modulus 1 million. But what about this document ID? I have this dollar postfix. And in this case, I'm going to feed just this bit to the sharding function, which means that both of these documents are always guaranteed to reside in the same bucket and hence on the same shard. So that under a very simple convention gives me a huge amount of benefit because I don't really have to think about that. I can just, okay, I know how it works and it's not complex and it's obvious. Why did you do that? Go away. Sorry about that. Okay, so we just hashed the highlighted parts and that's the convention, but nothing else. Now, let's talk about something more interesting. Now we have those ranges. Those are the buckets and they're all assigned to this shard or this shard. Now, I can do that in a global fashion, or I can do that using a specific prefix. So I can say something like, oh, all of the EU shards, all of the EU documents only reside on these two nodes, and this is the sharding strategy. On everything that does not start with the EU has this sharding strategy and resides in those. The key idea here is that we shard by the document ID. This is an immutable value. It's easy to, it's something that you always operate on, and it greatly simplified the overall system. There's no need for special configuration. You don't have to configure your sharding strategy or something like that. It's just going to work for you. It's also something that is very much in your face, which we found to be a really important property for creating systems that are sustainable over time. Another thing that this approach helps me with is this avoids many common issues. You can see here, this is a heat map of access to specific buckets. And some of the most common sharding issues is when you have one specific bucket that is very hot. And that's going to cause you a lot of pain, because we are doing that in a fair fashion. And again, the classic example is I have New York users, I have London users, I have, I don't know, Paris users, and all of my activity, my biggest customers are in London. And that's going to kill my system because I can't actually split the load across everything. Another common issue is that if you don't use the ID, then you might want to say, oh, I have a London customer, now they are moving. How do I manage that? And the most important thing is that, again, remember, I'm assuming Homer Simpson is using my system. So the idea here is that I want to do nothing to get the right behavior. I want you to fall into the pit of success by doing the right thing. And most importantly, because falling into the pit of success is great, but if you don't have the right capabilities, then you're just mired in, I don't know, the pit of gray expectations. A question so far? Okay, great. Oh, we have a question. So we have William. What is the benefit of collocating documents? So the most common example is this. I have this customer and the orders for this customer. I'm always going to be processing them together. So it makes a lot more sense that I can run them in the same location. Now, there is another aspect here, and that aspect is if I'm asking, give me the most recent orders for this customer, I know that they're only going to reside in that single location. So that means that I don't have to query all of the shards. I can just query one of them. And the next question is, what if a customer grows? Wouldn't that make a hotspot? It would absolutely do that. But at that point, you have a question to ask. How do you want to handle that? And you can say, oh, you know what? I'm going to say that my shard function is orders 1, 2, 3, customers 1, 2, 3, 9, something like that. So now you're sharding by the customer and the date. At this point, you lost the collocation with the customer's document, but you still have strong tie. So documents that are related are close together. You can make operations much faster. And this is important because remember that I talked about flexibility. Right now, I can change for all future documents how I should behave. I can also do something more interesting. I can say, oh, you know what? I need to update that. So I can go here and say, oh, I'm going to run a patch operation and delete and recreate the document under a different name. This looks something like this. I think like this. So previously everything was under orders. If I did this properly, and I'm really so I have different document IDs. And this, what I just did, resharded everything transparently and on the fly. So, oh, we have more questions. That's great. So you could locate them up to a certain size to get a performance, then patch to reshard and prevent hotspot from for fast growing. Yeah, I can do that. I would almost never need to do that, I think. Remember something very important. Many databases will tell you to start sharding once you're in the tens to low hundreds of gigabyte range. RavenDB is perfectly fine with terabyte range on a single node. And that would be the typical size of a database that you would only individual shards in a sharded database. So the hot node isn't that much of a problem from our perspective. Okay. But the whole idea is that even for that scenario, you still need to be able to operate in a reasonable fashion. Okay, now let's talk about another reason why I want to put everything in a single related documents in the same collocation. This is about running transactions. So RavenDB is a transactional database. You can make many modifications to different documents across collections, across documents, and have that happen in a single ACID transactions. With shardings, we are in a much more complicated state because now the data resides in multiple locations. So here's what we guarantee. We guarantee that if you're running on the same bucket, all of the changes are transactional. What happens if you're not running the same bucket? Well, they're not necessarily going to be that. So in this case, if I want to update customers and their orders, then I want to do it like this to make sure that they're in the same transaction. But sometimes I actually do want, and I do need transactions across multiple shards. And that is generally a really complicated feature. But RavenDB already have this notion of a cluster-wide transaction. So you can actually utilize that to get a cross-shard transaction. And that leads us to an interesting observation that you can choose on every operation basis what level you want. If I'm running a modification, some update on this sort of system, I don't need any cluster-wide transaction. This is already transactional by the nature of using the same bucket. But if I'm running in a cross-shard environment, I have to push data between two different customers. I can use the cluster-wide transactions and get what I want. Now, TF earlier said something about fault tolerance. And fault tolerance and sharding are actually orthogonal to one another. Remember that I show you this thing, which looks quite scary. So what's actually going here is that I have 3 shards, and they are running on different, each shard is replicated on 3 different nodes. This is a really strange thing to do, because in this case, just run it on because all of the data resides in all of the nodes. So just run it on non-sharded replicated data. But it gets interesting when you think that you don't have to do this one-to-one mapping. You can use just, let's say you have a shard factor of 3, but a replication factor of 2. And that actually gives you more capacity. And you can see how it works like this. We have a sharded environment, and each node has a different shard. And here's another database and same thing here. Now, this is orthogonal to replication, because if I have more nodes in the cluster, I can now have a replica of node win 2 or node E, a replica of node win 1 or node D, etc. And the whole idea is that instead of having to rebuild everything from scratch, we reuse the already existing concepts of database and ownership and how it works. Now, let's talk about queries and operations. So right now, RavenDB, you issue a query to RavenDB, give me a particular document. How does it do that? Let's see. I ask RavenDB to give me this document. What happened? How does it know what to do? Well, this is the document ID. We hash that. We get the bucket ID. We have the topology of the system. And in order to show the topology of the system, I have to do something that would probably give me an error. Let me see if I can do that easily. And error here. So I would have to do it like this. Okay, you don't like me. Here we go. So now you can see here, this is the actual topology that we have. Shard start at 0, shard start at this one, shard start this one. So what happens? I take this one and I compute what bucket it's at. And then I can just scan this and, oh, this is 500 million. So it belongs to this. And now I know that I need to go to shard number 1. Shard number 1 is actually this guy, and it belongs to these 3 nodes. And then I can do whatever I need from them. What happens if I do a query by ID? Again, same behavior. And query by ID looks something like this. Let's use employees, it's easier to remember. Yeah, it would help if I could actually spell properly. No, now it doesn't like us. From employees. That's annoying. Okay, sorry. I mentioned that we're going to get errors. This is supposed to be working. Basically it is that it should recognize that this is and handle that, basically do the same thing that same here. Hash ID, not the bucket, go, and you're done. Things become more complicated when we start talking about more complex features. So let's get the London employees. They reside in different shards because they belong on different document IDs. Now, and I want to mention, okay, how to manage that? We set it to the server, everything works. This is going to give an error. Yeah, well, but let's see something more interesting. From orders, group by employee. And now this is interesting because what happened here is that we execute an aggregation query. And how does it execute this aggregation query? Well, it sends it to all of the relevant nodes. And then it is able to say, hey, this is aggregation, and I can just re-aggregate the results again to give you the final value. And there are actually a lot of smarts around out how to merge the results, handle paging, ordering, all sorts of stuff like that. Sometimes you know better. Sometimes you know that I'm asking for all of the orders for a particular customer. but I know that this is the pattern of customer IDs, of orders for customer IDs. So I can ask RavenDB, utilize this for this query, only go to the shards that contain this document. So we slightly optimize the behavior. A key aspect that I have in the design is that I don't want to care about sharding. That means that all of the features of RavenDB that you've seen are meant to operate as they do in a non-sharded environment. There are a whole bunch of them. I'm not going to go over the list, but the basic idea is that the responsibility of managing the sharding is on the RavenDB cluster. It's also meant to be something that you manage on your own. And that leads to the probably the most complex part of any shard implementation. How do you modify that? Some databases just don't let you do that. Some databases takes forever to do that. With Raven, we decided that there are certain requirements that we have to meet. We have to make sure that this is a live operation. Not only does it have to be a live operation, this has to be an operation that doesn't impact general operations. So here's how it works. Remember that we talked about 1 million buckets? We didn't pull this number out of a hat. Here's what the idea here. If you divide a terabyte by 1 million, you get 1 megabyte. So for every terabyte of data that you have in the system, each bucket is about 1 megabyte. And by the way, William, that goes back to your questions about the size of buckets. A 1 megabyte bucket is probably not going to be a problem regardless. But let's say that I'm talking about 100 terabyte, a 500 terabyte data set. So each bucket is roughly 100 to 500 megabyte in size. And now we have this scenario where we need to rebalance the load or rebalance the data between the servers. What do we have to do then? Well, we have to move a bucket, and that is constrained and limited, and I don't have to do everything from scratch. So that means that I can, okay, let me copy this megabyte, this 10, 100, 500 megabyte, and I'm not having to rearrange all of the chairs on the Titanic. And I use that phrase specifically because if you're doing resharding of some other databases, they would rearrange everything and it takes forever. We're also able to accept some level of unfairness. If I have node A that is 10% bigger than node B and C and I have enough capacity, I don't actually care. There's no need to actually do that. Another really important thing, remember that sharding and replication are orthogonal, which actually means that when you look at this, node twin 0, this is not necessarily a single server. This may actually be spread across multiple different nodes. So you actually have a lot more capacity than you might expect. The other aspect is that, okay, we get to the unbalanced detection. We select one single node to move. And again, the whole idea is that we want to do that in an iterative, non-destructive process. We migrate the data. We basically take all of the data that is relevant, move it to the other location, and then delete it from the other side. Because of the data sizes, we are typically able to do it in a single batch, which drastically reduces the amount of complexity that you have to deal with. That also means, by the way, that you can manage that when you add a new server to the cluster, a new shard. Why is that? Okay, I'm sharding on 3 nodes, now I want to shard on 4 nodes. Well, the act of adding this new node to the cluster, now we're going to start slowly siphoning items away from the other servers to that one, but we're not going to break the world or do reshuffling of everything. We are planning on a beta release in a month or two. A lot of that depends on dotting all the I's and the T's. This is the stage where we're at now. As you saw, it has some rough edges, and I would deeply appreciate any feedback and commentary that you have to make, either now or feel free to send us to us afterward. I'm also sending my email on the chat, so you can ping me. And a large part of the reason for this, the reason that we have chosen to implement Sharding the way that we did it, is that we want to make it easy and simple and obvious to do the right thing. And with that, I would be very happy to answer any questions that you have.
When you're then moving a bucket between your different shards for that, would that be one which is on the edge of the domain? So you have a certain bucket set?
Yes. So you don't have to, but the way that we operate is that, let me just share my screen again and I can show you. Okay. So those are the ranges. And the basic idea is that this is actually sorted by the bucket range start. And the cheapest way to do this is to say, okay, I'm going to take either this bucket and move it to this one. I'm going to take the last bucket here and move it to this one. So basically, I'm either modifying this document, this value, or this value, incremented by one or decremented by one. And why does it matter? Because it gives me on the optimal number of ranges and I don't have to do complicated associations. Sometimes I would have to break it up and I have maybe more than 3 ranges that I have to work with, but that's hopefully not something that we did it too often.
Brilliant, thanks. Yeah, it makes sense because you don't just want like a comma separated list of a million different buckets.
Exactly. So the whole idea is that we want that you're always hitting this for operations, and this is assumed to be small because again we want it to be all in operation.
Yep, brilliant. Thanks.
Okay. Right. Any further questions?
Yeah. In that scenario where you were changing the document ID or sort of recreating the record to effectively do that, is there any assistance with things that are referencing that, or do you have to go and find those and update them manually?
In that case, so what I did, and you're talking about this thing, this is pretty horrible. Don't do that. So the typical way we do that, you would say, okay, I'm going to apply that only to new things, or I'm going to apply that to, and then I would have to think, okay, what is, for example, no one references documents. They are the end of the object graph. They reference everything else. No one else reference them. In many cases, modifying the document ID of something is extremely rude operation. You have stuff in the logs. You have audit trails that you have to do. You don't do that. So the typical way to manage that is, okay, I'm going to apply that to only the new values that I have. And the whole idea here is that you're not constrained to a particular sharding strategy. So previously, all of the document ID, all of the orders for a customer were always in the same bucket. But now we have this crazy customer that keeps buying and they fill up the buckets. So what we're going to do, we're going to add the month of the order to that, and that would give us still all of the orders in a particular month are in the same bucket, which allows to optimize certain queries and operations. But at the same time, we're no longer stuck on that. The reason this matters is that otherwise you would have to deal with, okay, how do I change the sharding strategy for old and new and migrate that, and that's become an incredibly involved process.
Okay, thanks.
Okay, wonderful.
Cool. So I think that's all the questions. So I've actually not used RavenDB before. It looks absolutely amazing. You mentioned if people want to go and have a play around with the beta version, what's the different options for installing it? Do you have like Docker images?
You can use a Docker. Docker, I think that the command is something like that.
So would that wouldn't be the beta version though, this new version?
No, I would have to send you that. I don't remember that off the top of my head.
Cool.
But it's something like that, and you have to select the right version for that.
Nice. Yeah, I've not actually used RavenDB before, but as I say, especially the tooling, it looks amazing. So I'm definitely gonna have to go and have a play with this. It looks really good.
Yeah, I want to show you one last thing. This is not about Sharding at all. This is just to give you some context about the API that you typically work with. And this is C# API. You're working with Lean, strongly typed objects, all of the whole thing, and dramatically reduce the amount of complexity that you have to deal with.
Sorry, I was muted. Very, very nice. Cool. So
Thank you.
yeah, thank you so much, Oren, for an amazing talk. We are going to have